Good day, my dear students. So today I am going to show you the solution to our problem set in dynamics. So starting on the first item, so we have a tug of war situation. That means that our object will be experiencing two opposing forces, one to the left and another to the right. So team A pulls with a force of 100 newtons on a side, and team B pulls with 90 newtons on the other side. Determine the net force of the rope. So you are required to solve for the net force. So you would expect that you would be summing the forces along the x-axis. So below is the free body diagram. So for team A, the force exerted is 100 newtons, and we put that on the right side, or the force is directed to the east, while the 90 newton is on the opposite side, directed to the west. So if we sum the forces along the x, since the forces are on that particular axis, so we will have a positive 100 newtons subtracted with a negative or with 90 newtons. So the difference will be 10 newtons. And since the net force is positive, the net force is directed to the east. In other words, team A is pulling with a greater force. The next problem is about a toy car, which is a tres. And then a force of 70 newton is applied to the toy car. So there would be an applied force present on the object. If a frictional force of 20 newtons is present, determine the net force on that toy car. So first, drawing the free body diagram of the toy car. Although it is not stated where the 70 and the 20 newtons forces are directed, in which direction they are directed, we will assume that the applied force is directed to the east, while the frictional force is on the other direction. So here is the free body diagram. When we sum the forces along the x to get the net force, what we will get is a positive 70 newtons minus 20 newtons. And the difference will be 50 newtons. The net force will be equal to 50 newtons directed to the east. On the third item, a couple decided to move the cabinet in their dining room. So we have two people pushing the cabinet. They stood on one side and each push left with 30 newtons of force. So their pushing force is the applied force. And you expect that you will have two applied forces since there are two people, a couple, right, pushing the cabinet. So since there's motion and the cabinet is moving across the surface of the floor, there will also be a generated friction force on the opposite side of, or in the opposite direction of the motion, equal to 10 newtons. Now you are again asked, what is the net force acting on the cabinet? So drawing the free body diagram, so each person or the couple would have a combined applied force of 60 newtons. That's why we have two 30 newtons forces directed to the left. And the frictional force is opposite that, 10 newtons. So to compute for the net force, you just sum the forces along the x. So 10 newton would be positive in your equation, while the two 30 newton forces will be negative. So if you get the sum of the forces along the x, you will be getting negative 50 newtons, or your net force is 50 newtons and it is directed to the west. For the fourth item, you have four free body diagrams here. Free body diagram A to D. And you are asked which of the following objects is accelerating. So if you are asked with this kind of question, one way to think about it is which object is experiencing a net force, since the net force is the one responsible for accelerating the object. So if any of these objects, A, B, C, or D, is experiencing an unbalanced force or a net force, it would be accelerating. So the thing to do here is to compute for the net force for each of the cases. So for the first one, we can see that the forces along the x and the y balance each other out. So the net force on both of the axes will be 0. That means this object is not accelerating. In object B, we can see the 225 newtons directed to the north and south will cancel out, but not the forces along the x. When we sum the forces along the x, 20 newtons minus 15 newtons will be 5 newtons. That's our unbalanced force. Since an unbalanced force is present, the object will be accelerating, particularly to the right or to the direction of the east. Object C only have two forces acting on it, both equal to 25 newtons. So both of these forces will cancel out, and this object will not accelerate. Object D will have a 20 Newton force directed to the right. So there would be an unbalanced force acting on that object equal to 20 newtons along the x. So this object will also be accelerating to the east as well. Now for object or for item number 5, we are to compute for the net force of this object experiencing 4 forces. So we have a 121 newtons force directed upwards, while downward there is a 196 newton force. To the left there is a 60 newton force, and we have a force of 150 newtons directed 30 degrees from the x-axis. So this is where your knowledge of vector resolution will come to play. So since you cannot add the 60 newtons with the 150 newtons, since the 150 newtons is not parallel to the x-axis. So in your summation, you should not simply sum 60 newtons and 150 newtons. You actually have to find out the x component of the vector A, so you can sum it with 60 newtons. And of course, there is also a y component of the vector A, so that you can also sum that with the 121 newton and the 196 newton forces. Okay? So let's just call 150 newton vector A. So looking at the diagram or the triangle, the right triangle that you were able to form, so if you superimpose the vector along the x and the y, this is the diagram, the triangle that you were formed. The orange one being the x component and the green one being the y component. So as you can see, the 30-degree Newton opposite of that angle is the AY. So you would expect that you will use the sine function to compute for the value of AY, since sine is opposite over the hypotenuse and AX is in the adjacent side. So you will expect that you will use the cosine function, since cosine is adjacent over hypotenuse, to compute for the value of AX. So doing the computation for AX first, so we have cosine adjacent of that angle, 30 degrees, is the AX, and of course the hypotenuse is vector A, 150 Newton. Multiplying both sides with or by A, so you will be able to cancel A on the right side of the equation, and there will be an A appearing on the left side. So A times cosine theta. So your A is 150 newtons, and your cosine theta, your theta is 30 degrees. Multiplying this will lead to an answer of 129.90 Newton, which is your A sub x. Okay? And then your a sub y, you can compute that using the sine function, since the opposite of the angle is the ay. So doing the same thing, multiplying both sides by a, you will cancel a here on the right side, and also multiplying on the other side will result to the equation for ay. So a times sine theta. So again, your a is 150 newtons. Multiplied with sine, your theta or your angle is 30 degrees. So the product will be 75 newtons. So again, it is not the 150 that you will sum with the 60 newtons if you want to do the summation of forces along the x, but the x component only. Okay, so showing the calculation, so you have a negative 60 plus the positive 129.90, which is the ax. The sum will be 69.9 newton. The net force along the x is 69.9 newton directed to the east. Meanwhile, for the summation of forces along the y, you have a positive 121 newton and a negative 196 newton, but also a negative 75 newton force. Okay, let me just fix this really quickly. So this should not be um, equal to negative 75, but it should be, I need to add the 75 since the ay is looking here is directed upwards. So we have just a mistake here. Let me add 121 with negative 196, and then I have to add the 75, which is the value of ay I just computed. So that means, okay. So the net force along the y is actually 0, is equal to 0, which works out since this gives us a conclusion that the object is accelerating to the right only, since we have a net force of around 70 newtons, or 69.9 to be exact, along the east. So the object will be accelerating to the east. Okay, on item number 6, we can use the formula for the second law of motion, which is the net forces will be equivalent to the product of the mass and acceleration. So here we are asked to solve for the unbalanced force that is needed to accelerate a 0.5 kilogram block. So that is the mass of the block. And we have two cases of acceleration at 4 meter per second squared and b at 8 meter per second squared. So of course, you will have to do two computations here. So for letter A first, so let's write the formula. Force equals mass times acceleration. The mass of the block is 0.5 kilogram. And then you multiply that with the acceleration, which in case letter A is 4 meter per second squared. So kilogram times meter per second squared is newtons, and 0.5 times 4 is 2. So your net force, if you have this particular acceleration, will be 2 newtons. Let's say it's to the east. And for case letter B, the same process will give you a net force of 4 newtons. And let's also assume that it's directed to the east. So this example is a very good way to illustrate the effect of a net force that you applied on an object. Okay, so we have the same object, but in the first case, you applied a net force of 2 newtons, and in the second case, you applied a net force of 4 newtons. So the mass is the same since we're talking about the same object. What will be the acceleration, the resulting acceleration? So that means, in other words, if you apply more net force on a particular object, it will result to a greater acceleration. In this case, it resulted to an acceleration of 8 meter per second, or a net force of 4 Newton resulted to an acceleration of 8 meter per second squared, while if that value is divided into 2 or is half of that, so a net force of 2 newtons will result to an acceleration of only 4 meters per second squared. In item number 7, similar scenario, similar situation, but you are solving for the mass instead this time. So solve the acceleration, no, rather, the acceleration, but you're given with the net force and the mass instead. If the unbalanced force of 84 Newton is acting on the following masses. So for the first case, it's 4.2 kilogram, and on the second case, it's 8.4 kilogram. So modifying the equation, when you're given with net force and mass, so acceleration will be the quotient of that net force divided by the mass. So for the first case, 84 newtons will be divided with 4.2 kilogram. So newtons divide that by kilogram, your resulting unit will be mass, or will be meter, divided by, or meter per second squared. So 84 divided by 4.2 is 20. Again, let's assume it's to the east. And for the second case, doing the same process, but this time dividing the force 84 newtons by a larger mass, 84 or 8.4 kilogram, what you get is half of the first acceleration, half of 20 or 10 meter per second squared east. Now this is example, or this item is another way of showing the implications of the variables. Ano po? If we have the same net force acting on two objects, but one of the object is lighter and the other is heavier, the acceleration that will be experienced by the objects will be different. So for the lighter object, the acceleration will be higher, but for the heavier object, the acceleration will be lesser. Okay, so in item 8, we are again looking for acceleration, and we are given with a mass of the car, a 1,200 kilogram car, as well as its speed, 50 kilometer per hour, and it is experiencing air resistance. Air resistance is a kind of force equal to 5,000 newtons, and a road friction, so we also have a friction, 2,200 newtons, if the wheels push with the force of 7,500 newtons. So you're looking for acceleration. Your formula for acceleration is net force divided by mass. Your mass is given, it's 1,200 kilogram. You don't know the net force. So you would think that you would be summing forces, right? But your trouble here is you don't know which forces. We have 3 Newton forces here in the item number 8, which would be directed to the right and which would be directed to the left. To figure that out, just think of which object, or which force rather, will lead the car to move forward, and which forces will oppose that forward motion. So obviously it is the wheels responsible for pushing the car forward, right? So we will say that 7,500 Newton in the free body diagram would be directed to the right. Friction, of course, is a force that opposes your motion. So that should be on the opposite side. Your 2,200 Newton will be to the left. Air resistance is just another term for friction. So you are actually looking at two types of frictions here on your problem. So it should also be directed to the left. So your air resistance would be a result of air molecules bumping on the moving car. So you have two forces to the left and one force to the right. So if you sum the forces along the x, what we get will be 300 Newton, unbalanced force. So the car is still moving forward, okay, to the east or to the east. And to use our equation for acceleration, net force divided by mass, the division of 300 newtons divided by 1,200 kilograms will be an acceleration of 0.25 meter per second squared to the east. In item 8, you are again solving for acceleration. So a certain force, you have a clue word here, and that means you will be solving for the force. Accelerates a 3.2 kilogram mass by 2.4 meter per second squared. So you're given with mass times acceleration. Multiplying the two will give you the value of that force. Now, we have a follow-up here. What would be the acceleration of a 1.6 kilogram mass when the same force acts on it? So that means you will also be applying that force on another object, which is lesser in mass. So that means that you would expect that the acceleration of the second object will be greater since the mass is lesser, right? So it would be good to first note the given and separate the given for object 1 and object 2. Also take note that the force acting on both objects are the same. So we have a note here that the net force on object 1 is equal to the net force on object 2. For object 1, we're given with mass and acceleration. So we can easily solve for the net force acting on object 1. So since that is the same force acting on object 2, we can then solve for the acceleration using the formula net force divided by mass for the acceleration of object number 2. So solving for the net force for object 1 first, 3.2 kilogram times 2.4 meter per second squared is 7.68 newtons. That is also the net force acting on object 2. And now we can use the acceleration equals net force over mass formula, 7.68 newtons divided by 3.2 kilogram will be equivalent to an acceleration of 4.8 meter per second squared, which is greater than A1, which is only 2.4 meter per second squared. Okay, on item 10. So again, this is a multiple step item. So you would have to do several steps to come up with your final answer. So a 7.2 Newton force accelerates mass 1 by 5 meter per second squared or meter per second per second. So here, what you should be realizing is you're not given with the mass, but at least you're given with the force and the acceleration. So you can still solve for the mass of object 1. The same force, which is 7.2 Newton, acts on mass 2 and impart to it an acceleration of 20 meter per second squared. So again, you're not given with the mass, but you can easily solve for that. What acceleration will the same force meaning 7.2 newtons, impart to the two masses when they are joined together? So you will be adding mass 1 and mass 2 to get the total mass. And if the same force, the same 7.2 force is imparted on that combined mass, what will be then the acceleration of that combined mass? So again, taking note of the given, separating the given for each of the masses. Okay, starting at mass number 1 first. So net force is given, acceleration is given. The formula for mass will be the net force divided by acceleration. So when you divide Newton divided by meter per second squared, that is will lead you to a unit of kilogram. So 7.2 divided by 5 is 1.44 kilogram. So that's the first mass, 1.44 kilogram. Now, for mass 2, the net force is the same, 7.2. Acceleration is higher, so 20 meter per second squared. So you would say that mass 2 should be lighter, right? So if we divide that, this should be mass 2. Mass 2 is only 0.36 kilogram. So again, if we sum mass 1 and mass 2 and apply the same force, 7.2 Newton, what would be the acceleration? So 1.44 kilogram plus 0.36 kilogram is 1.8 kilogram. 7.2 divided by 1.8 is 4 meter per second. So finally, you were able to arrive with your final answer, which is the acceleration of the combined masses, or mass 3, as we note here. Okay, now, so in item 11, you have to find the missing values. We are given with a situation here that there is a 2 kilogram box at rest on a table. So I have to find the acceleration, the net force, and the value of the individual forces acting on the object. So we have to draw a free body diagram first, right? So since the object is only at rest, or since the object is at rest on a table, the table will be exerting a force, an upward force on the object, which is manifested here as the normal force. And since the object has a mass of 2 kilogram, it would have a weight, or a gravitational force acting downwards. So these are my only forces acting on the object. You can easily find the gravitational force since that's only mass times acceleration due to gravity. Your mass is 2 kilogram, and you multiply that by acceleration due to gravity on Earth, so 9.8 meter per second squared. Your weight, or your F sub g, or your gravitational force, is 49 newtons. So the object is at rest. That means it's not accelerating, or the acceleration is 0. Therefore, there are no the the forces cancels out or balances out. There is no unbalanced force. The net force is 0. If you sum the forces along the y, so Fn and Fg should be equal to one another. So Fn is positive, subtract that by Fg. The sum of the forces should be equal to 0. The net force is 0. So that means the net force is equivalent to the gravitational force, which is 49 newtons. For item 12, similar situation or similar approach. We have a 2 kilogram box, but at this time it's not at rest. It's sliding to the right across a table, and it is experiencing a frictional force equivalent to 5 newton. And I have to find out its acceleration, its net force, and the value of the individual forces, again, acting on the object. So since it is sliding on top of a surface, the table, it should be experiencing a normal force from the table. So it has a mass, that means it has a weight as well. It's mentioned in the problem that it is experiencing a frictional force since it is sliding across the table. So again, we can compute for the weight, the gravitational force easily. Again, it's equivalent to 49 newtons. It's sliding to the right. That means the net force is present along that axis and not on the vertical axis. So that means Fn and Fg cancels out. They have the same value. So if you sum the forces along the y, it should be equal to 0. So the net force is equivalent to your gravitational force for the forces to cancel out. So your normal force is also equivalent to 49 newtons. So it is the weight of that object, of that 2 kilogram box, pushing on that table. The weight is equivalent to 4.9 newton. As a reaction to that weight, as a reaction to that push down, the object will react by exerting an upward force of the same magnitude but opposite direction, but in the opposite direction. Okay, that's the law of action-reaction, third law of motion. So as a continuation, we have to find out the net force. The net force is present along the x-axis. Since friction force is the only force on that axis, that's already the net force, or it is the frictional force causing the unbalanced force, okay? Or causing the acceleration of the object. Acceleration can be computed using the formula net force divided by the mass. So we have a negative net force, negative 5 Newton divided by 2 kilogram. The acceleration is, that should be negative 2.5 meter per second squared, or 2.5 meter per second squared directed to the west. On the item number 13, we have an elevator. So that means we're expecting tension here. A 5 kilogram freight elevator is moving upwards towards its destination. Near the end of the ascent, the upward moving elevator encounters a downward acceleration. So we're given with acceleration 2 meter per second squared, and we have to find out the net force and the value of individual forces acting on the object. Again, since we have an elevator, we're expecting for tension to be present in the free body diagram. Since there is an acceleration, I should be able to compute for a net force. My net force should not be equal to 0. So this is my free body diagram. We have a tension lifting the elevator up, and of course it has a mass, so it has a weight as well, or it is experiencing the gravitational pull of the earth, as all objects with mass are experiencing, including us. So the net force can be computed easily, no? Since we have the value of the mass and the acceleration, which is downwards. So let's put a negative on that 2 meter per second squared. My net force is, of course, also negative. The direction of the net force should be the same as the direction of the acceleration. So 500 times 2 will be 1,000 newtons. That's my net force. So since I have my net force, I can compute for the value of the individual forces. So for the weight, just the log again of my mass times the acceleration due to gravity, 500 times 9.8 will be 4,900 newtons. So you would expect that the weight will be greater than the tension for the object to accelerate downwards, no? Since that will lead to an unbalanced force directed to the south or downwards. So if I sum my forces along the y, my tension is positive and my weight or my gravitational force is negative. So I already computed for my net force. So I will put that on the left side of the equation, since the left side is the summation of forces, or my net force or my unbalanced force, which is negative 100 newtons, equal to tension, I don't know my tension, minus gravitational force, which is equivalent to 4,900 newtons. So if I put this on the other side, it will become positive. Negative 1,000 plus 4,900 newton will be 3,900 newton. That's my value for tension. Again, my weight is greater than my tension. That's why there is an unbalanced force directed downwards, and the elevator is accelerating downwards because of that particular unbalanced force. Okay, on item number 14, we have already a free body diagram. And net force, or normal force rather, gravitational force and frictional force are not given, or are unknown. Net force also unknown. And acceleration, also you have to solve for the acceleration. But we are given with the mass, 5 kilogram mass, and the coefficient of friction, which is 0.1. So looking at this diagram, free body diagram, you can easily solve for the gravitational force, right? since it's only the mass times the acceleration due to gravity. So my gravitational force will be 4.9 newtons. From the free body diagram, it looks like my net force is present along the y. And again, just as most cases, my gravitational force will be equal to my normal force. The forces along the y-axis cancels out. Okay, so my normal force will be also equal to 49 Newton. This is the equation. This is the computation showing that. I have to solve for the normal force to compute for the frictional force, since frictional force is the product of the coefficient and the normal force. So my coefficient of friction is 0.1 and the normal force is 49 Newton. So the product will be 4.9 Newton. That's my frictional force. Since that is the only force present along the x-axis, that is the one causing the acceleration. No, or that is already the net force. Negative 4.9 Newton since it's directed to the left. Okay, so we can already solve for the acceleration here. Acceleration will be equal to the net force divided by the mass. The net force is negative 4.9 Newton divided by the 5 kilogram mass. So 4.9 divided by 5 will be 4.98. Newton divided by kilogram, again, is meter per second squared. So my acceleration is also negative, or to the west. Same with the direction of the net force. Okay, item 15 is the same type of problem. So you will approach it in the same way. So we have four forces present on the object: normal force, gravitational force, applied force, and the frictional force. So right here, you're given with the mass of 5 kilogram and acceleration of 2 meter per second squared. So already you can solve for the net force. Also, you are given with the coefficient of friction, and it is equal to 0.1 as well. No unit for the coefficient. But let's first solve for the gravitational force. Again, it's 49 Newton since we're given with the same mass. And we will assume that the forces along the y cancels out again. So along the y-axis, when we sum the forces along the y, it should lead to 0. That means the normal force exerted on the object by the surface is equivalent to its weight, which is 49 Newton. So again, you were able to compute for the normal force. That means you can solve for the frictional force by multiplying that by 0.1. Your frictional force is 4.9 Newton. There's no way for us to solve for the applied force without first solving for the net force. So solving for the net force, mass times acceleration, 5 times 2 is 10 newtons. Why is that? Because we can already sum the forces now along the x. So the frictional force is negative, and you will add the applied force positive. My net force, I just computed for my net force, which is 10 newtons, equal to my frictional force, which is negative 4.9 newton. Now, I can solve for the applied force. So putting the 4.9 on the left side of the equation will transform the sign to a positive 1. So 10 plus 4.9 is 14.9 Newton. That's the value of my applied force. So there you go. You were able to solve for all of the forces or all of the unknowns. Okay, item 16 to 20 will challenge you to draw the free body diagram of the object shown in the figure rather. So we have an object and it is hanging by a ceiling through the use of let's say cables or ropes. So how will we draw the free body diagram for this object? So of course the object has a mass, obviously, so we expect that there will be a gravitational force, and it's getting it is hanging on the ceiling because there is an upward force lifting it. So it can hang mid-air. That would be the tension. So the free body diagram of the box will look like this. But you can also account for the tensions T1 and T2. T1 has an angle from the ceiling equal to 60, while T2 has an angle from the ceiling equal to 40 Newton. So you can also account for that, T1 and T2. For item 17, we have an object with a mass of 10 kilogram getting pulled um, using a string wrapped around a pulley. So how will we draw the free body diagram? So already we know that it's resting on a surface, right? So we expect that there will be normal force. Of course, it has a mass, so gravitational force will also be present. So we have normal force and we have gravitational force. Okay, so the trouble here is, where do I draw the tension, or where do I draw the applied force here? Do I draw it to the right, or is it directed to the right or to the left? So we can see that the string is attached to the left side of the box. That's why the applied force is directed to the left as well. The applied force will be the one responsible for moving the box to the left. And since it's moving to the left, the frictional force will be opposite of that direction. The frictional force will be to the right. Okay, so on item 18, we have two masses, object B and object A. So object A is smaller and it is on top of object B. Object A is also attached to a string, let's say, on its right side. It's attached to the wall through a string on its right side. Meanwhile, object B is getting pulled to the left. There's an applied force on object B. So how are the forces on the two masses, A and B, interacting? Or what are those forces present on both of them? So I have to draw a free body diagram for both of the objects. So I guess we need to draw the FBD for object A first. So it has a mass, obviously. So it has a gravitational force downward as well, always downwards. Since it is resting on the object B, or it is on top of object B, it is object B experiencing that weight. As a reaction, it will exert an upward normal force on object A, which you can see here. There is a string on its right side, so the tension should be to the right. When you pull the object B, object A will go along with object B, but it cannot move very far since it is attached to the wall through the string. Okay, through the string. So it's also moving to the left, but um, there's a limitation to its movement since there is a string not allowing it to, let's say, to ride on object B to the left. So since it's moving along with object B to the left, there's a frictional force to the right. And what is that force pulling it to the right together with object B? That is the force of object B exerted on box A, on object A. Okay, so you will just do this labeling. Force um, box A, on A right here, due to or exerted by box B. Okay, since box B is getting pulled to the left. So force exerted by box B on box A. That's the notation. How about box B? So the same, there is a gravitational force on box B since it has a mass, and there's a normal force exerted by the floor on box B. But the normal force on box B is larger than the one on box A, since this is a reaction, or this is the reaction of the surface or of the floor on the combined mass of box A and B. So that's why here on the weight here, on the FG here, I put A plus B. Okay? Since the normal force exerted on box B is a result of the combined masses or the combined weight of A and B. So it's getting pulled to the left. So your applied force is to the left, of course. So you would expect that the frictional force is opposite of that. And since object B is acting on object A, there's a force exerted on box A due to box B. In the same way, on box B, there will be a force exerted by box A. So, force exerted by box A on box B. Same magnitude but opposite in direction. Okay? Okay, on item number 19, we have a pulley system here. We have also a ramp. On the ramp is mass 1, while mass 1 is attached to mass 2 or to mass 2 by means of a string, and mass 2 is hanging. So I guess it's easier to do a free body diagram for mass 2. Essentially, it looks like the one with the elevator, right? So we have a tension, the force responsible for keeping it hanging. Opposite in direction is the force of the weight or the force of the gravitational force, the gravitational pull of the Earth on this particular object. Okay, mass 1 is on an incline or on a ramp. Of course, there is also a tension force, the same tension force as in mass 2, since it is the same string connecting the two of them, right? Let us say that mass 2 is accelerating downward, and it is pulling mass 1 upwards. That's why the frictional force right here is to the left or downwards the incline, since the tension here is accelerating mass 1 upward the incline. So the frictional force will be opposite that. Gravitational force is always straight downwards, although or even if the mass is on an incline, but the normal force will always be perpendicular to the surface. So that's why it looks like this. Okay, so for the final item, you are to draw the free body diagram of two masses, mass 1 and 2, both of them on a ramp, and they are connected through the means of a string or a rope. So let's do first mass 1. So mass 1, again, we have a tension here. So it's getting pulled downwards by mass 2 by means of this tension or this tensile force. Since we assume that it's accelerating downward, it's moving downward, we have a frictional force due to the interaction of the molecules of the bottom of this mass 1 with the surface of the ramp. Okay? So opposite of the motion is the frictional. Direction of the motion is the direction of the frictional force. Again, as a while ago, gravitational force will be straight downwards, and the normal force will be perpendicular with the surface. Mass 2, okay, the same. We have the normal force and the gravitational force. The tension here, it's getting pulled upward by mass 2. Okay, so the tension on mass 1 is the same tension present on mass 2. So since it's pulling mass 1 with it, it's slowing its acceleration. Ano po? And you can see that here, due to caused by the tension or being pulled by mass 1, by the weight of mass 1. Since mass 2 is also moving downwards, down the incline, frictional force is opposite that. So upwards frictional force. Okay, so that's it for our problem set. I hope you were able to answer it. Good luck with your exams.